Welcome back to Mathematics for Economists. In this video we will learn about the properties of determinants of square matrices and how to calculate the determinant. Determinants are defined for square matrices, meaning that the number of rows in the matrix has to be equal to the number of columns. The determinant of a square matrix is a number that satisfies the following properties. First, the determinant of the identity matrix has to be 1. Second, switching two rows or two columns multiplies the determinant by -1. In other words, changes the sign of the determinant. Third, multiplying a row by a number multiplies the whole determinant by that number. And finally, adding any multiple of one row to another does not change the determinant. Note that this first criterion is needed to ensure that the determinant is unique, because otherwise we could say that the determinant of every square matrix is 0 and then the other three properties would still hold. The second criterion, together with the first one, implies that negative determinants are possible. The third criterion implies that if a matrix has a full 0 row or column, the determinant will be 0 then. For example, let's calculate the determinant of a general 2x2 matrix A, B, C, D. So first, I could multiply the first row by C, but that would multiply the value of the determinant by C, and I compensate for that by dividing by C, so that these two sides are equal to each other in the first equality. Second, I do a very similar thing with A and the second row. At the third equality, I invoke the fourth property of the determinants, meaning that I can add or subtract rows from each other. So I subtract the first row from the second row. At the next equality, I divide the first row by AC. Next, I take out a multiple of AD minus BC in front of the whole determinant from the second row. Notice that if I were to multiply this back into the second row, I would get the previous determinant, so these are equal. And finally, I subtract A over C times the second row from the first row, giving me the identity matrix. And by the first property, the determinant of the identity matrix is 1, so all in all we got that the determinant of this general 2x2 matrix A, B, C, D is just AD minus BC. Some examples of 2x2 determinants. Observe that the determinant of the matrix 3, 7, -2, 5 would be therefore 3 times 5 minus 7 times -2, which is of course 15 plus 14, giving us 29. Likewise, the determinant of the 2x2 matrix -2, 5, 3, 7 would be 7 times -2 minus 3 times 5, giving us -14 minus 15, altogether -29. Notice that I got the second matrix from the first one by switching the rows. As expected, the determinant got a negative sign as a result. Finally, the determinant of the 2x2 matrix 3, 7, 3, 7 is 21 minus 21, which gives us 0. So we have this rule for calculating 2x2 determinants, and we can derive a similar rule for 3x3 matrices as to how to break them down to 3 2x2 determinants. But we will also look at the generalization of this claim later. A convenient way to calculate 3x3 determinants, and not larger determinants, but only 3x3, is something we call the rule of Saurus. So in the rule of Saurus, we take the first two columns of the matrix and write them next to the 3x3 matrix, or we take the last two rows and write it under the matrix. Doesn't matter. Some people teach it this way, some people teach it that way. Both will give us the same result. And for these kind of northwest southeast direction diagonals, we multiply them together. and leave the signs unchanged. This is what these pluses stand for. And for these southwest, northeast diagonals, we likewise multiply all the elements together in one diagonal and then change the sign. This is what these negative signs stand for. And finally, we add all of these terms together. Now let's take a look at this matrix as an example, and I will calculate this by both of our rules for 3 by 3 matrices. Our previous rule said that I need to take the first row and then break it down like this. And then using these elements as weights, I can break down the 3 by 3 matrix into 3 2 by 2 matrices by having alternating signs in front of these 2 by 2 determinants, adding them all together. So here I take the elements of the first row as weights and put them in front of these 3 2 by 2 determinants, deleting the first row and first column from the original 3 by 3 matrix in the first case, deleting the first row and the second column from the 3 by 3 matrix for the second determinant, and finally deleting the first row and last column in the third 2 by 2 determinant. Calculating these 3 2 by 2 determinants is at this point very easy. I take negative 2 times 0, which is 0, and then subtract from it 1 times 6, giving me negative 6 for the first determinant. Then for the second 2 by 2 determinant, I multiply 0 by 0, which is of course 0, and then subtract from it 1 times 6, which gives me a negative 6 for that determinant. And finally, for the third 2 by 2 determinant, I take 0 times 6, which is of course 0, and then subtract from it negative 2 times 6, which is negative 12. So subtracting negative 12 from 0 gives me positive 12. And then I crunch the numbers here, I get negative 72. Now let's do the same thing with the rule of source. So I copy the first two columns right next to the original determinant, take the products of these diagonals in here with a positive sign, and then take the products of these off diagonals or southwest northeast diagonals, multiply them together and take those with a negative sign. And at the end of the day, I will be left with likewise negative 72. Now let's generalize this first algorithm a little more. To do that, we need the concept of minor matrices. So let's pick an element in the matrix A and then delete the row and column which this element sits in. So therefore I will get a one smaller square matrix. So instead of a 3 by 3 matrix, I will get a 2 by 2 square matrix, for example. Taking a look at the first example, I picked the element 1. So this red row and blue columns will therefore disappear, giving me the minor matrix 5, 6, 8, 9. Likewise, if I pick the element 4, that would mean that I need to delete the first column and the second row, giving me the minor matrix 4, 6, 7, 9. And similarly for these two other examples as well. Now, using this concept of minor matrices, we can expand the determinant of a larger matrix using the weighed determinants of the minor matrices along some row or column. So first, let's pick a row or a column. Then the determinant of A can be expressed along the ith row like this, or along the jth column like this. So notice that we are going through that row, taking the elements as weights, and also adding signs appropriately in front of these weights, and then multiplying these together with the appropriate minor determinants, and then adding everything together. Mathematically, it doesn't make any difference whether or not I pick the first row or the second column or whatever, but usually it is smart to pick a row or column that has the maximal number of zeros in it. Now, I realize that this is a mouthful, so let's take a look at a bunch of examples. So here we have this 3 by 3 determinant that we are interested in calculating. I've added these plus and minus signs to indicate which element will get which sign as a result of these -1 to the sum power. Then let's take the elements as weights, and finally include the determinants of the appropriate minor matrices. So when I'm at this 0, I will remove the first column and second row, so we'll be left with this minor matrix. When I'm at this middle element, I remove the second row and the second column from the 3 by 3 matrix, leaving me with the following 2 by 2 determinant. And finally, when I'm at this -3, I remove the third column and second row. Now we already know how to calculate the determinant of these 2 by 2 matrices, so we can crunch the numbers from here, and at the end of the day we will get 51 as a result. Let's observe this following other example. So here we chose to expand the 3 by 3 determinant along the third column. So this would give us the following expression. Again, we have these -1 to the 1 plus 3, 2 plus 3, 3 plus 3. Yeah, this is actually supposed to be 3 plus 3. The weights in front of them in blue, and then finally the appropriate 2 by 2 determinants. And if we crunch the numbers, at the end of the day we'll be left with, I highly encourage everyone that you actually crunch the numbers here to see that you get the same result. We can do similar calculations with larger matrices as well. So here in this 4 by 4 example, I picked the first row. This enables me to break down this into 4 3 by 3 determinants, which I already know how to do. And if you crunch the numbers, at the end of the day, you should get 588. Again, I encourage everyone to crunch the numbers here. Finally, a very special case of a 5 by 5 determinant. Let's observe that under this diagonal, every element is 0, so it makes sense to pick the first column or the last row to expand the determinant. And all but one of these determinants will be multiplied by 0, so I can just take -3 times the appropriate minor determinant. And I'll be left with a 4 by 4 situation that is very similar to the previous one. I pick the last row to expand my determinant, and that will make me pick up a multiple of 7 along the way, and I'll be left with this 3 by 3 matrix. Continuing on, we get that the determinant of this 5 by 5 matrix is actually just the product of the main diagonal elements, giving us 210. Now let's take a look at some rules of determinants, how they interact with algebraic operations. First, a non-example. It is not true that the determinant of the sum of two matrices is the sum of the determinants. So we cannot use this as an identity because it's not true. It is, however, true that the determinant of the product of two matrices is the product of the determinants. The following couple of claims are easy to verify. See for yourself if you can give reasons as to why they would be true. For some of them we already have seen examples. So the determinant of a square matrix is actually the same as the determinant of its transpose. If A is so-called a triangular matrix, so for example if under the main diagonal every single element is 0, or above this main diagonal every single element is 0, then the determinant is just the product of the main diagonal elements. Next, if we have a full 0 row or column, then we can show that the determinant is in fact 0. If two rows or two columns are equal to each other, then we can show that the determinant is 0. And finally, if we take an n by n square matrix and multiply the whole matrix by lambda, then it will multiply the determinant by lambda to the nth power. So this is it for the theory on determinants. In the next video, we will be looking at solving systems of linear equations. See you there.